Welcome to Chapter 1, Lesson 1, using a problem-solving plan. The objective for this lesson is to present to you a four-step plan to solve problems, particularly word problems. The other objective is to choose a method to do a computation with. Today's vocabulary is conjecture and inductive reasoning. Conjecture is educated guess, and inductive reasoning when you make a conjecture based on a pattern of examples or past events, something that most of us do every day without knowing it. Today's four-step problem-solving plan is 1. Explore, 2. Plan, 3. Solve, 4. Exam. In Explore, you're asked to read the problem quickly to get a general understanding of it. Some of the things you're looking for is what is the question being asked, what facts have I been given, and another thing to think about is, have I been given enough information to solve the problem? Come up with a plan. Some people prefer to reread it to see if what facts that they have in front of them. See the relationship between these facts. Come up with some sort of plan, some sort of conjecture or educated guess. And then come up with an estimate of your answer so you have something to check after you solve it. When solving, use your plan that you came up with. Sometimes you might have to rework it, especially when you check your estimate to your answer. And that comes up with exam. Maybe your answer is reasonable and it's close to your estimate and you're satisfied with the answer. If it's not reasonable, or your estimate or your answers are way off, maybe you should try again. Alright, here is our first problem. Our first word problem is, how much would it cost to mail a 9-ounce letter first class? So, exploring, I noticed that I have to find the cost of a 9-ounce letter. I've been given a table which shows the weight in ounces and the costs. And the table goes from 1 ounce to 5 ounce. Next, I'm going to come up with a plan. I'm going to use the table and hopefully find a pattern from the table. Quickly looking at the table, I come up with an estimate of about $2.30 that I think it might cost. To help me solve, I rewrote the table so I can see if there's a pattern a little bit better. I know at 1 ounce the base price is 37 cents. From 37 cents to 60 cents, the 2-ounce letter, I noticed that it increased 23 cents. Examining 2 ounce to 3 ounce, I see the pattern again, 0.23 or 23 cents. And a quick examination from 3 ounces to 4 ounces, once again I see 23 cents. Now that I have found my pattern, I believe I can come up with some sort of solution to help me solve and find out how much 9-ounce letter costs. 37 cents is the cost for 1 ounce. Now that I have 1 ounce, I need to add 8 more ounces. Using the pattern, I'm going to take 8 times 23 cents to give me the total of 9. 8 times 0.23 is $1.84. Add that to 37 cents. And the cost of a 9-ounce letter is $2.21. As I examine my answer, as you can see in the second table, it does seem reasonable. 23 cents added to $1.29 to get 6 ounces. Therefore, I follow the pattern all the way to 9, $2.21. Alright, our next slide, we have 2 problems. The first one, A, find the next term in 1, 3, 9, 27, 81. Best way to solve this type of problem is find a pattern, usually using some sort of operation like adding, subtracting, multiplying, or dividing. There are other patterns, but right now we'll start off with this. 1 to 3. My first guess is that probably we're going to take 1 and multiply it by 3. Let's see what happens when we take the next set, 3 to 9. I notice that multiplying by 3 also works. I'll continue on to the next set, 9 to 27. multiplying by 3 again. The pattern is multiplying by 3. So to find the number after 81, I will continue with the pattern. So take 81 and multiply it by 3. The answer then is 243. Our second problem, B, states draw the next figure in the pattern. It looks like I have 5 squares. In those 5 squares is another square that is shaded. I notice that from one square to the next, the shaded square seems to be moving counterclockwise. So I come up with some sort of pattern based on that counterclockwise. And using the last square, I believe that it should move down here. So let's examine that. Let's see if my answer is reasonable. I see the square has moved down here to this one. Then it moves over to give me this one. It goes up to give me this one. It moves to the left to give me this one. So I'm going to assume that we're going to go back to the original square and it should move down. Seems reasonable to me. Here's our next problem. The graph shows the seating capacity of certain baseball stadiums in the United States. About how many more seats does Comerica Park have than Fenway? By exploring the table and the question, I need to know how much more seating Comerica has than Fenway Park. I find Fenway Park and Comerica Park on the table. Also in my plan, I noticed that the question says about. That allows me to use rounding and estimating, two concepts that you should have fair knowledge of. Comerica is 40,000 seating, and there's really no need to round this, but I will rewrite it over here for this problem. Fenway is 33,871 seats, and I'm going to round that to about 34,000. Now I'm going to estimate, and I'm going to use the operation subtraction because I believe that subtraction will give me the difference in seating, and the difference in seating is about 6,000. This does seem to be reasonable because 34,000 plus 6,000 is 40,000.